Let's talk acids and bases. Seems like we've been talking about acids and bases for a while. Let's actually finally get to it. You know, the concept of an acid has been around for over 2,000 years because the word acid itself comes from the Latin word that means sour. So originally things that were sour tasting. Okay? So that's where that comes from. Also a long time ago, the concept of sour things turning litmus extracts red was common. You know, we use that for litmus paper now, but that's been known for quite a while. Here, why don't you name some acids for me? What's an acid?
Hydrochloric acid.
Okay. That's the most famous of all the acids because that's in your stomach, right? Acetic. We will be seeing acetic acid a lot. HC2H3O2.
Vinegar, right?
Yep, that is the acid that's in vinegar. That's usually the way its formula is written. Let me draw its structure.
Does vinegar and intermediate have an intermediate reaction?
No, vinegar is just 5% acetic acid. I mean, acetic acid, 5% solution in water, and that's pretty much what vinegar is. Okay, but that's the structure of vinegar. It's usually written HC2H3O2 for a couple of reasons. The only H that's actually acidic is this one. So what functional group is this? C double bond O, OH, remember? Yeah, this is a carboxylic acid. So this is an organic acid, carbon-containing compound, and organic acids usually are carboxylic acids. So usually it's written like this because it has the single acidic hydrogen, then the whole rest of it is the acetate ion. So we see HAC written very commonly. I'm going to put that in parentheses as an abbreviation because the acetate ion is abbreviated AC minus. So acetic acid. So we'll see it written in several of those ways throughout this chapter. We use that as an example because that is a very commonly used weak acid. We'll define the differences between those, but that's a weak acid. Hydrochloric acid is a strong acid. But I don't know, you may see CH3 COOH. No, let's write it right here. All the same thing. CH3CO2H. All of those are describing acetic acid. The acetate ion is different from acetic acid because it's missing the H plus essentially. Okay. So that's why we call acetic acid HAC sometimes. Okay. What's another acid? Hydrofluoric. Did we talk about hydrofluoric acid? Yeah. I very consistently refer to hydrofluoric acid as one of the only acids that actually scares me, even though it's a weak acid, which is so interesting. I think we'll probably talk about this later, but the rundown is if you get a strong acid on your hands, you know it immediately, right? If you get hydrochloric acid or sulfuric acid, H2SO4. If you get a strong acid on your fingers, you feel it burning. I mean, it almost feels like an electric shock. It triggers every nerve ending in the entire region simultaneously, and you immediately know it, and you can immediately go rinse it off, and you can usually be okay if you rinse it off right away. But hydrofluoric acid is a weak acid, so you don't feel it immediately until it has already seeped down into your skin and started to dissolve your bones. And the fluoride ion is also terrible for you. You'll learn about that in physiology. That can stop your heart. So hydrofluoric acid spills, it doesn't even take much. There have been fatal hydrofluoric acid exposures to people that don't really even realize that it got on your skin. So that's why hydrofluoric acid is scary to me. It's like the stronger acids, you know exactly what you get. You can prepare for them. You know if there's any contact, you can deal with it, and but yeah, that's why. You should avoid hydrofluoric acid. I would recommend that. All right. So those are some example acids. Bases have a bitter taste. Anything that we know as bitter is our tongue reacting to things that are basic, so like dark chocolate and coffee and usually if you take a prescription medication and you touch it to your tongue accidentally, it tastes all bitter and gross. So that's because of usually organic bases. Okay? Well, bad coffee can be kind of bitter, but yeah, not like good Starbucks sort of stuff.
Almost like a 4.5 pH.
Yeah, it can be a little bit acidic, but the bitter nitrogen the nitrogen-containing compounds are responsible for the bitter flavor of it. So, but yeah, it is slightly acidic overall. But, so they turn litmus blue, the other color, so you can use litmus paper to determine acids or bases. Let's do the 3 types of bases that you'll need to be able to identify. Ionic hydroxides. These are sort of our standard bases: sodium hydroxide, potassium hydroxide, calcium hydroxide. And because hydroxide is 1 minus, you have to balance it with the cation. That's why it's got CaOH parentheses 2. As an aside, something like CH3OH is not basic, because that is not an ionic hydroxide. That is an organic compound with an OH group on it. What were those called? This is an alcohol. Organic hydroxides are alcohols. And they're not basic at all. Okay, so ionic hydroxides, metal and OH minus. Metal plus OH minus. Metal 2 plus OH minus. Okay. So carbonates and bicarbonates. Okay. So the carbonate ion looks like that. What is the bicarbonate anion? How is that different? Has an H, so it's HCO3, and it's actually an H plus that was added, so it's HCO3 with a single minus. Okay. And we'll talk about how that's different and so on. So sodium carbonate Sodium bicarbonate.
That looks familiar.
Yeah, that's baking soda. Okay. Both are bases. Baking soda less so, okay, because it's already had an H added to it. Calcium carbonate, which is in calcium carbonate is in it's limestone, the main component of limestone. We're going to talk later on about how limestone is dissolved by acid rain, but that's because calcium carbonate is a base. All right, and then so we got
Is there a form of bicarbonate or something similar that makes a buffer? Buffer?
oh yeah, that's the main pH control of your blood.
Yeah.
The carbonate bicarbonate or the bicarbonate which one is it? Yeah, it's those two, okay, that control the pH of your blood. Yeah,
Well,
absolutely.
controls the pH, but so
Stabilizes
it
the
brings it
pH.
in the other
Mhm.
direction.
Yeah.
Sort of stabilizes, but
Yep.
it's not like a chemistry traditional buffer, is it?
Oh yeah, absolutely.
Where it, like where we did the experiment in the fall, where you put 1 drop in and that's enough to change it, but you put the buffer in and then you have to put 20 drops in before it
Yeah.
changes pH.
No, it's
that kind of
pretty
buffer?
that's pretty much it. Yeah.
Okay.
In chapter 16, we're going to talk for about a week about buffers.
We'll get there.
But yeah, a buffer's purpose is to resist changes in pH. So it has something that'll be able to react in either direction to allow the pH to stay within a certain range. But yeah, that's how your blood is able to maintain its pH. Other ones are organic amines. What is an amine? What element does an amine contain? Yep. Yep. So NH3 is ammonia. That's the simplest. Okay. We can replace any of those H's with R's. Okay. To have methylamine or trimethylamine or triethylamine or whatever. Okay. Most pharmaceuticals are amines. We drew pictures of several of them that contained nitrogen. That would be, so sometimes they're called, I don't know if you'll ever run across this word, alkaloids. Alkaloid is just another word for an organic amine, but they are basic, and we'll talk about where the structure, where that comes from. But for now, it has a lot to do with that lone pair of electrons on the N. You'll notice all these other things were negative, right? Like OH minus, or the 2 minus on the carbonate, or the 1 minus on bicarbonate. But amines are neutral, but it's that pair of electrons that serves as the basic component to those. Okay. So we'll talk more about those three as we continue.
Amines include the amides?
Not necessarily.
Okay.
No, I would focus more on just the R groups and, yeah.